This is our fourth theory lesson for our unit on waves for Physics 11. And in this particular lesson, we're going to be taking a look at some things called diffraction gratings and the single slit and double slit interference pattern. It's actually just a bit of an introduction, getting us ready for treating this in much more detail in Physics AP. So for today, we're just kind of getting used to what the pictures look like. And then in Physics AP, we dive a lot more into why do the numbers do exactly what they do. But I want to show you just kind of a general picture of how the layout works for where we're shooting for by the end of the lesson, just so you can get a feeling for what's where in the actual story. The overall plan is we're going to take a laser that's going to shoot out some light. And in the case of the classroom laser, it's some red light. The wavelength for that laser light is incredibly tiny, very, very tiny. It's less than a millionth of a meter, okay, less than a thousandth of a millimeter. Very, very small wavelengths. And we're going to shoot the beam a short distance until it hits a little opaque card, about the size of a playing card, like in a card deck or an Uno card. But cut in that card is going to be a little slit for that light to go through. And the laser light will be wide enough. They're usually a few millimeters wide. It'll be wide enough to actually illuminate all the way across the slit from left to right. The slit, for when we're playing this game, can be very, very small. You can imagine something often as thin as a human hair. So very, very tiny. And then we're going to watch and see what happens when that laser light goes through that very, very narrow vertical slit and then travels several meters across the classroom. Okay, so this L that I'm talking about here could be a couple of meters, or it could be half a meter, it might even be 5 meters, but some nice distance across the classroom where it's going to hit a screen. And I'm going to just tell you the answer right now so you can see what we're shooting for. If it's a laser beam hitting a single slit that's oriented vertically, you actually see the beam smear out sideways, and it forms just this band of light from left to right. What's interesting, and one of the things we're going to talk about, is the fact that there's some little gaps along the way where the light doesn't seem to hit. And it's pretty predictable where those gaps will be. And you'll be able to look at a pattern like that when you see this little smearing out band and go, oh yeah, there's a single slit somewhere. That's what the light's going through. And that's what waves do when they go through a single slit. They smear out, plus they can have these little spots where nothing shows up at all. Another thing that we'll be shooting for today is what happens if we take the laser beam and send it through 2 slits. What if these are, perhaps, like I said, maybe as wide as a human hair? And they're very close to each other, so close that the laser beam, which is a few millimeters wide, can actually hit both at the same time. And we'll see that the pattern changes a little bit. It's still smeared out from left to right. It actually still has these little gaps where nothing shows up at all. But instead of being a continuous smear from gap to gap, it's actually a whole bunch of little dots from gap to gap. So again, the single slit looks like this, smeared out, but with some little patches of nothingness. And the double slit with 2 slits looks like this, smeared out, patches of nothingness, but dots instead of general thick bands. We're also going to talk about something called a diffraction grating. If you can imagine trying to set this up where you're trying to get the laser to hit these 2 little slits that are as wide as a human hair across, it can be a bit of a daunting task getting the alignment right. So sometimes it's easier to take that little obstructing card and just cut just hundreds of slits in it and have the laser beam hit 3 or 4 at any given spot without any real easy aiming or any tough aiming. So the pattern for a diffraction grating, it turns out it looks exactly the same as the pattern for 2 slits. So it can be 2 slits or 3 slits or 4 slits or 5 slits, however many the laser's wide enough to hit, and they all look the same. And if we ever talk about a diffraction grating today, it is like a sewer grate, but it's down the size of a little playing card with little slits cut in it. Sometimes, again, the size of human hairs. And then you go several meters away to see the pattern that shows up on the screen as it smears out. Well, let's write a few notes in. Actually, not a lot of notes today, a lot less compared to last day. First thing, let's just talk about how light, when it goes through these openings, how it's going to smear out. Now, thinking back to that first picture, I want you to imagine that you're up here on the roof kind of looking down, bird's eye view, looking at this slit from the top, and then the laser's coming in and then spreading out. That's what's happening here. So this is the bird's eye view looking down on the slit, which might be very, very narrow, as wide as a human hair. And the waves are going to come in. And what we'll notice is there's a change depending on how big the opening is. And I've left in the notes here that diffraction in general is going to be two things that we should be aware of. First thing is just this spread, that it is going to spread out as long as the opening, the slit, is narrow enough. If it's wide, then the beam comes out in a nice straight collimated beam. So I'm going to use the letter A to talk about how wide the hole is, right? A for aperture. That's how wide the slit is. Could be as thick as a human hair. And in this picture here, it looks like that opening is quite a bit bigger than the wavelength that we've got for that light that's actually going in. And so what you'll find is if the opening is substantially bigger than the wavelength, it's not just a strict inequality here where it's like, oh yeah, it was 5% different. If it's substantially bigger than the wavelength, then a big opening will cause very little spread. It's like waves going through a very large opening in a breakwater in a marina. You just see them come out as a beam. As you narrow the size of that opening down, when that opening size gets around the size of the wavelength, it could be a little bigger, but when it gets around the size of the wavelength, that's when you're going to notice this spreading out. So the beam is starting to kind of diverge, if you wish, right into like this nice little fan. And it gets more and more aggressive, like a really impressive spread, if you've got an opening that is really small. So if that opening is way down there at around the size of that wavelength or smaller, you should expect to see a lot of spread for that light when it comes out of that opening. And that is why, looking back at my first little graphic, that is why we see this smearing out from left to right. So it comes out and then it smears left and it smears right to cover the whole screen. But it does have these little patches of nothingness along the way, right? Where there's no light hitting, little patches of darkness. And that's the other issue that we should probably talk about just in terms of what is diffraction all about. So issue number 2, there are some dark areas. There are some places where you don't see any light hitting at all. And we actually number these dark areas in physics so we can keep track of which one's which. Working from the center out, the first one you find on either the left or the right side is called m equals 1. And then the next one out is m equals 2. And I have to be honest with you, by the time you've gone past m equals 2 for most experiments in a classroom with a laser beam, you're not going to notice the beam anymore after that. The spreading gets so faint you can't see it. So if you can kind of find the location of the first and the second dark patch on either side when you're looking at the picture like this, find these first and second black spots on either side, you're doing actually quite well. All right, so looking down, bird's eye view again. A is the size of the opening, could be as small as a human hair, and then L is going to be the distance to the screen. That actually might be several meters, and then here's stuff happening on the screen. All of this could happen within a few centimeters. And what we're going to do is keep track on the screen. Maybe we'll take a ruler and start measuring from the center. We're going to call that distance where we see stuff happening, we're going to call that x. And those values for x could be a few centimeters big. So what do we have? A is the size of the opening. I've got an angle off to the various patches. The angle off to patch 2 of darkness is bigger than the angle off to patch 1. And filling in very few little spots in your notes, A is going to be that slit diameter, that opening, right? How wide it is, probably around the size of a human hair. And the equation to try to figure out where the dark patches are, the equation from physics, which we'll look at a lot more in Physics AP, is one that tells you the angle off to that dark patch. And it says A, the size of the opening, the aperture, times the sine of the angle is equal to m, which is just an integer, depending on which patch you're trying to find, multiplied by the wavelength for your laser. So if you wanted to try to find, as this picture shows, the angle off to dark patch 2 from the center line, you would put a number 2 in right here. If you want to try to find the angle off to dark patch number 1 right there, that would be theta 1, then you would put a 1 in for that m. So the m is just an integer. It's like a name tag that lets you know which one you're looking for. So that's diffraction in general. You send something through a small opening. and it's going to end up fanning out with some dark patches along the way. But now for the last part of the day, let's move beyond just a single patch, which fans out light with some dark patches. And let's look at a double or triple or quadruple, right? What if you have more than one opening? Then the laser beam is going to hit these openings, and each one of them will fan some light out. So I'm just going to take a second here and see if I can pull up a little graphic for you that we saw last day. So here was that picture we looked at last day for talking about interference. And this is what's going to happen with the laser beam. The laser beam could be coming in from your left, and it's wide enough to hit a couple of openings, and then each one of these openings behaves like a little speaker of laser beams, like a speaker for music that fans out music in every direction. These little openings, as long as they're tiny enough, right? They have to be down near the wavelength of light. That's why they need to be like, the size of a human hair, around that size. Then they're going to actually fan out the light. But if the upper one here is fanning out light, and if the lower one is fanning out light, then there could be places several meters away on the screen where the interference pattern could be very impressive, where the light could be hitting with a lot of amplitude because you have constructive interference. But then there are other places where you get nothing, and then a good spot again, and then nothing. So constructive, destructive, constructive, destructive, constructive, destructive. And that's why you get all these little dots where it's like dot, 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 dot. And every dot is where the light is interfering in a good, constructive way. And every spot between the dots is where it's not interfering in a good way. But we're still going to find that there are these general couple of patches of darkness where the light can't seem to do anything at all. And we talk more in Physics AP about why it does that. But let's look at this picture here and see what it's going to look like in terms of the math now for the double slit, right? For when the story has two slits and we have all of these dots. All right, so I'll find my notes here. There we go. Just before we hit that deal looking at the two dots, let's look just a little bit of Math 10 for a minute, a little bit of SOHCAHTOA, to try to figure out how we can measure these x's, these distances on the screen, once we know the angle from the physics, and L, the distance from the obstruction off to the screen. So again, L is going to measure the distance from the obstruction over to the screen, probably a couple meters. The physics is going to give us an angle, and we might want to know if we took a ruler on the screen exactly how far sideways things would be. Well, it's really just tangent from right angle trigonometry. The tangent of the angle that the physics equation gives you is just going to be the distance sideways divided by the distance over to the screen. So we just have opposite divided by adjacent as we're working through this. Okay, the multiple slit interference pattern. So you have this in your notes. We have all of the little dots happening where it's like dot, 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 dot. And what I have not drawn in this picture, not yet, I haven't drawn in anything about the little patches of darkness that you can actually see happening like right here or right here. So let's ignore those for a minute and let's just look at all of those little impressive dots that are happening along the way. So D, that letter D, is going to talk about the distance from the middle of one opening to the middle of the next. Now remember, these openings, they could be the size of a human hair, and it'll be a little bit bigger than that when we go measure how far it is from one to the next. And you'll see a lot more information mathematically about this in Physics AP for why the math does this. But here's an equation that will let you locate any one of the dots from the center out. We actually number them with integers, little name tags, but this time I'm going to use the letter N for these intense bright spots. And you have an intense spot right in the center at n equals 0. And the equation that predicts the angle to the bright spots, it looks exactly the same as the last one to predict the dark patches, but instead of A for aperture, we put in D, the repetition distance between the two openings centers there. So if you wanted to try to find the angle that's shown here, angle number 3 off to the third bright dot, then what you would do is you would put a 3 in for that N. You'd multiply it by the wavelength for the laser, and you could divide by the D, and that would give you the sine of the angle, and then you could inverse sine it. And so again, you would be finding the angle off to, measuring from center, you'd be looking at like the third little dot out, right? So somewhere out there. And if you really wanted to know the x value for it, well, then you could do that tan theta is equal to x divided by the L. Okay, well, let's put everything together. Imagine you've got some sort of diffraction grating. So I can see that it's a grating, right? Because they're saying the word right here. That just means like that sewer grate. So it's going to have something that looks kind of like this. And these gratings have a hole size for each hole, that's the A, and then a D, the distance from hole to hole. And they want us to imagine what it would look like to draw this on the screen. Now your notes are pretty much almost complete, but we'll just fill in a few things and you can see how this game would actually work. If I was doing this, I might want to just keep track of all the different variables here, because there are so many different sizes, and some of them are, smaller than a human hair, and some of them are like the size of a classroom. So L is going to be the distance from the screen to the obstruction. I'm going to go 5 meters for that based on what they've said. And the wavelength for this laser, it says 632 nanometers. Well, I look on my formula sheet to see what nano is, and it says, that's 10 to the negative 9. Okay, great. So 632 times 10 to the negative 9. It is tiny. It's less than 1,000th of a millimeter across. A is going to be the size of the slits, pretty tiny again, okay, 10 to the negative 5. Not as small as the wavelength, but small enough. It's getting tiny, small enough to make some nice fanning out of the light. And the D, the distance from opening center to opening center, a little larger again. Okay, so I'm going to start off by finding those dark patches. You can actually do this in either order, but I'm going to try to figure out where are these places located where there's just these patches of nothingness. So I've got m equals 1 and then m equals 2, and I'm going to go and see where they're located on the screen. So I try it out using my two equations. I'm going to put in m equals 1 to find out where the first patch is. And the physics comes back and it says, look, I've got an angle for you. It's not even 1 degree, so it's not fanning out all that much, 0.92 degrees. And the physics just likes to give you that angle. That's what it specializes in. And if you're asking, well, how would it look on the wall if I walked over to the wall? If you want to talk about x, the distance along the wall sideways, now you need some math 10. So I'm going to take that 0.92 degrees and put that in here for my angle. I'm going to put it in my 5 meters away, and I get a pretty short distance. So it's 8 centimeters to the side. That's where you're going to find the first dark patch. So again, looking at the picture, from the center, right, if I measure from the center out, I only have to go 8 centimeters until I find the place where the dots are going to disappear for a little while. Now, the second dark patch, this is one of those, do as I say, not as I do things. I'm going to get a little bit lazy here and show you a sneaky way to do this. Officially, I should tell you that this is nonlinear, meaning that it doesn't follow a perfect pattern. But it almost does. So officially, you should go and try this again, putting in a 2 in here, coming up with the angle, and then putting that angle in here and seeing what the x value is. But it is almost linear, meaning that if it's 8 centimeters to the first dark patch, it's pretty much going to be double that to the second one. It's not perfect, but it's really close. Close enough that that's what I'm going to do. So keeping track of the dark patches, if patch number 1 is at 0.92 degrees, it's double whatever your calculator was saying for patch number 2, and it's going to be 16 centimeters to the side for patch number 2. Pretty much perfectly doubled, so close that you can go with it. So great, now we know where the dark patches are, but we need to figure out where are all the little dots going to be. No problem. Let's find the bright spots. I don't even have to do the first one. If I want to get a little creative, if I want to just do something different, I could say, hey, why don't I find the third dot to the side? Just for fun. Where is it located? I can find where the 7th one is, the 11th one, whatever I want. I'm going to try to find the third one. So I put in that 3, that integer here. And when I use the equation, which we'll look at more in depth in Physics AP for why it's true, I see that the angle is about 2/3 of a degree to get to dot number 3. So I'm actually finding from the center out where the third dot's actually going to be located. Not the first, but the third, just because I wanted to do the third. Okay, doing a little math 10. I find that the third dot is actually located 6 centimeters to the side of center. Now remember, it's not perfectly linear, but it sure is close. So if it takes 6 centimeters to find the third dot, if you had found the first dot, which maybe made more sense to do, but if you had found the first dot, it would have been 1/3 the way over. So not 6 centimeters, but only 2 centimeters. So the dots go 2 centimeters, 4 centimeters, 6 centimeters, and so on. They're just going to follow that nice, beautiful little pattern. So you've got this little table in your notes. And again, there's no particular reason why I did the third one. In fact, I only did the third one instead of the first one just to show you that I can. So the third one, 6 centimeters to the side, it's going to follow an almost linear pattern like this. So if the third one is 6 centimeters to the side, the first one would have been 2. The second one, 4. The fourth one, and we're going to talk about this one more in a minute, would be at 8. The fifth one, 10, and so on, just every 2 centimeters. But there's an issue, because unfortunately, this fourth dot, which is trying to show up 8 centimeters to the side, unfortunately, it's in the location of that spread out fan of light where there's a dark patch. I know that from just the earlier page in your notes, from back here. Yep, there is a dark patch of nothingness at 8 centimeters and another one at 16. So when we have this table all filled in, it's like, yeah, that was gonna work, but unfortunately, this one's gonna have trouble showing up. Oh, and this one too. So you'll see a bright dot right in the center, and then as you work your way out, either to the left or to the right, at 2 centimeters, 4 centimeters, 6 centimeters, but you won't see one at 8. Then you'll see one at 10, one at 12, one at 14. You won't see a dot at 16. It's unfortunately in a dark patch. And then another one at 18. And then by around then, just usually a little bit after the second dark patch, it's really, really hard to see this fanned out little stream of dots of lights. So on the screen, we're going to end up with something like this. So in red, I've shown the little laser dots showing up. Right in the middle, you'll get a nice impressive little dot, and then every 2 centimeters there will be a dot. But unfortunately, the dot that was trying to be bright, intense dot number 4 ends up being where dark patch number 1 is. So it just gets obliterated, taken out. And likewise, over at the 8th intense dot, it's just unfortunate that that lined up perfectly with dark patch number 2. So I'm using, again, the letter capital M, or sorry, lowercase m, to talk about which dark patch we're talking about, and lowercase n to talk about which dot we're looking at. And that picture there is kind of the classic pattern you're going to see for 2 or more slits. It could be 5 slits, 3 slits, 7 slits, but it's more than one. Okay, one slit would be just a band of light. In fact, I'll draw it right here. If it was a single slit, it would look like this, just a smeared out beam, and then a smeared out little stream here with a dark patch, it would look kind of like that. So the lower one is the single, and then 2, 3, 4, or whatever you want. After you're at 2 or above, you're going to see little dots of constructive and destructive interference for the multi-slit pattern. And that's it for our interference lesson. And that's our second to last one for this chapter. That's also going to have a little bit of quantum mechanics for the final lesson that we're going to do. Oh, no, wait, I stand corrected. There was one last little thing that we were going to look at. Just a little add-on. Since it's the last time to do a lesson on waves before we do quantum mechanics, I just wanted to talk really briefly about polarization, something we'll talk more about in Physics AP. But imagine taking a slinky and sending some waves through like a fence that has a little vertical opening in it, and you're trying to send waves with different orientations to them. If you were to try to send waves that were oriented vertically for their side-to-side motion through a vertical opening in a fence, then those waves would be allowed to pass. And that fence is behaving as a Polaroid filter that's only allowing waves of a particular orientation to pass. If your fence had a vertical opening to it, but you tried to send in left-right wiggles with your slinky, it would get totally blocked. So waves that are not aligned with your Polaroid filter, when you have this polarization issue going on, they can't actually get through at all. Just a little thing to note, I'm not going to do too much on this. Just one final little thought. Only S waves, side-to-side waves, like light, can be polarized. Sound waves that are push-pull, they cannot. But a little bit of trivia just as we finish. Because light waves, which are S waves, can be polarized, that's how we can have 3D movies. When you wear your 3D glasses, those are special Polaroid filters that allow the movie company to actually project two separate movies on the screen, one for your left eye and one for your right. And those 3D glasses are oriented in a way where the light from one of the movies being projected on the screen can only get to your left eye. And that's the view for your left eye. And it was shot actually with two cameras when they were taking the pictures for the movie. And then the image for your other eye, for your right eye, it's oriented the other way. And it's also put up on the screen. That's why it looks so confusing if you take the glasses off, because there's two separate movies being played. And then the right-hand movie goes just to your right eye because it can get through that Polaroid filter, which is oriented the right way. It's slightly more technical than what I've got here. It's not just an up-down, left-right polarization. It's a special deal called circular polarization, which means you can, lean your head over to the side and you still see the 3D movie the way it should be. But it's still a polarization issue. And that is going to mark the end of this lesson.